Well, I'm extremely happy for receiving this prize in the year of my 70th birthday. I studied electronic engineering. After electronic engineering, I had a Master of Science in electrical engineering and a PhD in systems and computation. And both my advisors, my MSc and my PhD advisor, both of them were former students of Lucian Pollack from Berkeley. So naturally, after my PhD, I came to Berkeley to study with Lucian. And he was the person who mostly influenced my career. So I thank Lucian Pollack for his help in my career. 10 years later, I came back as a visiting professor in Berkeley. And that was the time when Karl Marx had published his algorithm, and I got absolutely mad about it. So I worked for 6 months, day and night, because I was convinced that he had not reached the bottom. Okay. So instead of talking about my career, I would like to amuse you a little, telling a bit of what happened before Farid, by the time Farid was in his diapers, with complexity in continuous optimization. Well, I met Leonid Kashин using my usual trick for meeting Russians. I went out for a smoke and he was puffing up there. While we were talking, while we were chatting, George Danzig came and said, "Oh, I would like to meet this young man." The young man was him. And so they met, and I reached for my camera. It was not there. But then Keith Rose came a little later and took this picture. So this was 5 minutes after I met Kashian and Asilomar. Well, what I want to talk about, and maybe amuse you a little bit with this, is some drawings, some pictures of what happened before integral point methods. So the Russians, if you look at the book, very simple, very easy to read book by Nemirovsky and Yudin, you find there, well, I see that those who have tried are laughing now. You study complexity in schemes that are composed of a class of problems, an oracle, and a stopping criteria. I'll show this by showing the very general problem of finding of convex feasibility or optimality. The setting is, we start with a large convex set containing unit ball and a small set with a radius epsilon. Question is, find a point in the target set. We assume that we are capable of computing the center of gravity of that set, and then we call the oracle. The oracle finds a separating hyperplane that separates this set in two parts. It's known that the volume of these two parts are approximately equal. So when you cut, what you get here is about one half of the volume. So you can now you can repeat this. Find the center, the gravity center of gravity. Cut, and then you cut in a smaller piece. So this is the best possible algorithm. It's impossible to do a better algorithm, and this defines the complexity of the scheme. So the complexity is the performance of the best possible algorithm. And in this case, we know, and this, what you need is, you must cut it. Each time you cut it by 1/2. So what you need is logarithm of 1/epsilon cuts, but not 1/epsilon because this is a ball and epsilon the radius. So it's n times logarithm of 1/epsilon iterations. Calls of the well, this was too difficult. Since you cannot do this, you must work with figures for which you can find the center of gravity. And these figures, let's go directly to the figures, are ellipsoids. So you start with an ellipsoid, let's say a large ellipsoid, and this set is the target set where you want to find a point. And then you do the same thing as before. You find the center of the ellipsoid. Well, this particular ellipsoid is a ball, but it's an ellipsoid. You find the center of gravity, which is the center of the ball, and you cut as you did before. Now, doing it again, finding the center of gravity of the half ball and cutting it is often as we had before. But what you do is you construct a new ellipsoid that contains this half ball with the minimum possible volume. It's an easy thing to do. It can be done with n-squared operations. Okay. And that's it. Now you cut again. Let's do some iterations. So let's see this iteration. I start with a half ellipsoid, a containing ellipsoid. Now I forget the half ellipsoid. I stay with the containing ellipsoid, and I cut it in half. I cut it in half, and now construct the smallest ellipsoid that contains the half ellipsoid. And all this is very easy. Okay? One more iteration to end this. Ellipsoid with the target in there. Find the center and cut. And now find the new ellipsoid that contains that half ellipsoid. And this is the ellipsoidal method. In the ellipsoidal method, the computation of each new ellipsoid takes order n-squared arithmetical operations, and the worst case performance then is obtained by order n-squared logarithm of 1 over epsilon cos of the oracle. The former one was n log of 1 over epsilon. Okay, so this is a wonderful algorithm. And now comes the application of this algorithm to the linear programming problem. So this is the linear programming problem. Everybody knows the linear programming problem. The set is a polyhedral. So we have this polyhedral, and we must find a vertex of this polyhedral with the minimum possible cost. This is the simplex method. The simplex method by Danzig starts in some vertex, and then you see these are the constant cost slices, constant sets. So the cost reduces while you go from one vertex to the other until you come to this point. Well, it's a wonderful algorithm, but it's exponential in the worst case. Then comes the Kashan Sputnik. Kashan looked at the ellipsoidal method and applied the ellipsoidal method. Well, for the ellipsoid method, you need an epsilon. The great contribution of Kashan was telling us what epsilon is. So, and epsilon is 2 to the minus L, where L is the number of bits in the input. There are other ways of defining L, but this is a nice one. So what's L? You can't do this anymore, but you might get to a problem, put it in a tape, and measure the length of the tape. That's L. If you find a solution with precision so this is the epsilon, 2 to the minus L, you can purify the solution to an exact vertex, and all this is done in order n-squared L computations. Marvelous. This was first page of the New York Times. It really created havoc all over the world because people thought, Americans thought that he had found a Russian guy had solved the P equals in P, and so the Russians now could decode all the American codes, and they would win the Cold War. Well, they didn't win the Cold War, and the method was not good anyway, even for linear programming. It caused a revolution, but it was not a good method for linear programming. Now, there was an evolution. Some years later, in '84, Kamarkar wrote his projective interior programming method, and he reduced this from N4L to N3.5L computations, but now the method was usable. The method was good and solved big problems. I proved at that time that Kamakar didn't know nonlinear programming. He came from combinatorics. I looked at his method and said, this is a nonlinear programming method. And I proved that it was a steepest descent method using his potential function. Then I started working on this. I tried about 85 different paths to change this thing and nothing worked. Rennegar found his path-following algorithm without lowering the complexity, but he was the first to find a path-following algorithm using the QI centers, the idea of analytic centers. I started from a different path because I knew a lot of Fiacco-McCormick's barrier methods. So I used barrier methods. It was independent of the work of Rennegar, actually. And then at a workshop in Asilomar, Vaidya and I presented our algorithms with the complexity order of n cubed L. Vaidya followed Rennegar's method. I followed I used path-following method using the barrier function, and in a way I had more success than Vaidya. Well, my only formulas. So you have the linear programming problem, you have the feasible set, the barrier function. You see here we have x greater than or equal to 0. The barrier function, this is the logarithmic barrier function that everyone knows. And then we construct the penalized function, which is given for a parameter alpha. It's f alpha of x equals a combination of the cost and the barrier function. And then we define a central point as a minimizer of the penalized function. This is the penalty function, the barrier function. See? This is the analytic center, and this is a drawing of the central path. Now what we want to do is to follow this central path. To follow the central path, what we need is, I am at a point. I want to know how far I am from the central path, and then how do I do to get near it. And this is done. Now, we need a distance to a point. And the distance that's used is a Riemann distance, which is, it's equivalent to this. You take the point, change the scale to the point 1, 1, 1, 1, 1, and then measure the distance. This is what's written here. See? And there is a big theorem that says the following. If you're, let's call proximity to this distance. If you start with a point whose proximity to x of alpha, central point, is smaller than 0.5, in the simplest possible way, then after a Newton step, it goes down to 0.25. That's it. So your distance is 0.5. You take a Newton step, it goes to 0.25. And this produces this. So this is the complete description of the path-following algorithm. You have a parameter, alpha k. Let's assume that this point is near this one. It's in the beginning you find a way of forcing this. So this distance here is 0.25. Then you change the alpha k, and the change is very simple. It's a very simple formula. Okay, the formula is here. You change the alpha k. When you change the alpha k, your desired point comes here. And this distance now is 0.5. And you take a Newton step, and you get the distance 0.25. Well, that's the algorithm. And so this is the algorithm. It has the consequences that this alpha, the inverse of this alpha is connected to the duality gap. So the duality gap is reduced by 2t minus L, like Kashin wanted, in order of square root of n L iterations, and you do this in order in cube L arithmetic computations. So this drawing is definitely the best thing I did in my life, and and most probably the reason for my cash and price. Thank you.